Welcome to the shape of space. This lesson is on the Einstein notation, and I'll follow this up with several lessons on tensors which make use of the Einstein notation. Einstein notation, also known as Einstein summation convention, is a notational shorthand used in mathematics and physics, especially in linear algebra, tensor calculus, where we're going to use it in the next lesson, differential geometry, to simplify expressions involving summations over indexed variables. According to the convention, when an indexed variable appears twice in a single term and is not otherwise defined, it implies summation over that term over all the values of the index. So I have a very simple example here. This notation AI, BI is shorthand for the summation over I of AI, BI. This upper index is not a power, it's actually just an index. So AI should be understood as the ith component of A, and B sub I is the ith component of B. And we're just taking the sum over those, over the values of I. Sometimes you'll hear receive the term indicial notation. And Einstein notation is just a special case or an example of indicial notation. There's other examples of indicial notation. In fact, we'll talk about another one of the example in this lesson. The notation, Einstein notation, was in fact invented by Albert Einstein in 1916, and he was said to have humorously remarked on his innovation, stating, "I have made a great discovery in mathematics. I have suppressed the summation sign." Okay, so let's proceed and look at some examples. An index over which you sum over is known as the summation index. It's also called the dummy index, since any symbol can replace it. I have an example here. From our previous slide, we had AI, BI, and that's exactly the same as AJ, BJ. You can interchange with any index you like. An index that is not related to the summation is referred to as a free index. It should appear only once per term. So we have an example here. We have our AI, BI, and then we have a CJ. And since J doesn't involve this index here, we can write it like this. We just pull out the CJ, and then we have what we had before concerning the summation over AI, BI. So here's a few more examples. Here we have two summations. These first two are summed over I, and the second two are summed over J. So it's just the product of two summations. Here's another one. We have J is the summation index, and then I and K are free indices. And so the summation would be over J. And that's the same. I didn't write it in the notation here, summation, but since there was only three terms, I wrote it out fully. You notice it's A1, B1, and then we don't touch the free index. We just leave that as it is. You have 2 here and then 3. And then we have another one where we have 2 indices that are summation indices. And let's say we're going from 1 to 3. Then we would sum over the I from 1 to 3 and the J from 1 to 3. So we would get this double summation here. Okay, so on the next slide, I'll talk about some rules, and then we'll do some more examples after that. Let's look at the rules for Einstein notation. It's pretty simple. There's only 3 rules. Implicit summation over repeated indices. It's the first rule. If an index appears exactly twice in a single term, once as a superscript, known as the contravariant index, or once as a subscript known as the covariant index. Summation over that index is implied. Each index can appear at most twice, and if it appears a third time, then it's invalid. So we see here we have AI, BI, CI, so this is invalid since I appears 3 times in one term. Free indices must match on both sides of the equation. Indices that are not, I said this already, indices that are not repeated within a term are called free indices. If an index is a free index on one side of an equation, it must be free on the other side, and its position, superscript or subscript, must match. So here's one that's a little bit complex. You might think this is invalid because I appears 3 times, but the rule is in a term. So in this one term here, the I only appears once and the J is twice. That's our summation index. And it's okay if you have another term with I in it and another term with the free variable I in it. This is a valid expression. So the rules really apply one term at a time and across an equation. Now here's a problem. The second one is not valid because you have 2 free indices, but they don't match up here. You have an AI and a BJ. So this would not be a valid expression. And this expression here is also invalid since the free index I is not in the same position on both sides. So this is also out. The most common application for the Einstein notation is matrix multiplication or matrix times vector multiplication. And there's 2 ways of going about it. You can let the subscript represent rows and the superscript represent column, or you can invert that and let the subscript represent columns and the superscript represent rows. I'll show you both approaches in a couple of examples. The first example is AX equals B. A is a matrix, X is a column vector, B is a column vector. And we can represent it like this using Einstein notation, where Aij is element Ij of A, Xj is the jth element in column vector X, and Bi is the ith element in column vector B. Or we could switch the meanings around for what the subscript and superscripts mean. So in this case here, the subscripts relate to the column and the superscript relates to the row. And so this is equivalent to this with the change in meaning that I just mentioned. Then we can multiply matrices together. So C and A and B are all matrices. And you can represent it this way here, where we're taking the subscript to represent rows and the superscript to represent columns. And then this is summation over K. So in order to get element Ij of C, you're multiplying row I of A times column J of B. And again, you could shift the meaning here where the subscript represents your columns and the superscript represents your rows. And so this is equivalent to this with the change of meaning I just mentioned. We have a couple more examples. You can multiply a row vector times a column vector. So we're letting the subscript represent a row, the superscript representing a column, and you get the dot or inner product. So this is equivalent to this. The trace is even simpler. If you write AII, that just means the sum over I of all the diagonal elements in A. The Kronecker delta function is defined by this notation here, delta ij, and it equals 1 if I equals j, and 0 if I doesn't equal j, and I as well as j range from 1 to n. This comes up in the Einstein notation several places. I have a few examples of that. So if you have delta ii, that's the sum over I of delta ii. And since you're going from 1 to n, this is just adding 1 to itself n times, so you get n. For an n by 1 vector v, you can multiply delta times that, and then you just expand it out as shown here. And this is 0, this term is 0. The only term that's not 0 is delta jj, and that's 1 times vj, and you just get vj. You can multiply the Kronecker delta times a matrix. I have that here, or at least one element of the matrix here. And so you sum over m, and the only time this would not be 0 is when m equals I, and this would be 1, and this would be aij. We can apply the Kronecker delta function to itself, like this. And so when m equals I, you get delta ii, so that's 1, and then you get delta ij, and so that would be the product. You can take the standard basis for Rn. We need to write it two different ways. So if we take the inner product as a row or a column times either the opposite, a column or a row, then it's just this here. In other words, when I and j are the same, you get 1, and when they're different, you get a 0. We have another indicial notation on this slide. It's often used with the Einstein notation. It's called the Levi-Civita symbol, or Levi-Civita epsilon. It represents a collection of numbers defined from the sign of a permutation of the natural numbers 1 to n for some positive integer n. And I'll go to the details down at the bottom of the slide. It's named after the Italian mathematician and physicist Tullio Levi-Civita. Other names include the permutation symbol, antisymmetric symbol, alternating symbol. But what I've seen is that the Levi-Civita symbol is the most common by far. So we'll go with that name for the notation. So basically you have a set of n numbers from the natural numbers 1 to n. And then this symbol basically gives you a value based on what these numbers are. So there's three cases. If these numbers are an even permutation, and I'll explain what that is on the next slide, the value is 1. If it's an odd permutation, the value is -1. And if it's not a permutation, then it's 0. So this set here doesn't have to be a permutation. For example, if m was 3, you could have 1, 2, 1, and that's not a permutation. That's, it's a collection of 3 numbers with repeats from 1 to 3, but it's not a permutation. So you have 0 in that case. On this example and the next, I'm going to give a quick review of permutations. This was the notation I used on the last slide, and what that means is we take the numbers from 1 to n and we permutate them such that 1 gets mapped to a1, 2 to a2, and then to an. Sometimes this is written in a longer form like this. I think this is easier to see. And a particular example may help. Here we have n equals 6, and then you can see the mappings from 1, 2, 3 all the way up to 6 to a different arrangement. We could also write this in cyclic notation. Notice that 1 gets mapped to 4, 4 to 6, and 6 to 1, so that's a cycle. Then we have another cycle, 2 to 5, 5 to 3, and 3 to 2. So that's a second cycle. And we can write this way here in terms of the product of 2 cycles. You notice I use commas between the elements in each cycle to distinguish it from this notation here. That's pretty standard. Then we have one other example. I'll just use n equals 3 here to make the point. But if you have 1, 2, 3, and you map 1 to 1, 2 to 2, and 3 to 1, this is not a permutation because you've mapped 2 things to the same element. and you need to have all different elements in this rearrangement. So if we look at our definition of the Levi-Civita function, basically this would take this this mapping, not a permutation, this mapping, and it would assign it the value 0. Okay, so we still have the question of what's an even or odd permutation, and I'll talk about that on the next slide. So let's get to the distinction between an even and odd permutation. Every permutation can be decomposed into a composition of cycles. I mentioned that before. An even permutation can be obtained as a composition of an even number, and only an even number, of exchanges called transpositions of two elements, while an odd permutation can only be obtained by a representation as an odd number of transpositions. And by definition, a cycle with only two elements is called a transposition. So the key idea here is that there may be more than one way of representing an even or an odd permutation in terms of transpositions. It always has to be an even number of transpositions that represents an even permutation and an odd number that represents an odd permutation. So I have an example here where n is 4, and we have 1 to 3, 2 to 4, 3 to 1, 4 to 2. So we have two transpositions, two cycles of length 2, I should say. So this is an even permutation. Then we have some rules here. I won't prove them, but they're basically effectively theorems. The following composition rules apply for permutations. The composition of two even permutations is even. In other words, multiplying them together. The composition of two odd permutations is even. The composition of an odd and an even permutation is odd. And from the above, it follows that the inverse of every even permutation is even, and the inverse of every odd permutation is odd. Okay, so we have a number of mechanisms to determine whether we have an even or odd permutation. And I'll work through some of this in the case of n equals 3, which is one of the more common cases because this is used a lot in physics where you're talking about three-dimensional space. Let's look at the case for n equals 3. We have the Levi-Civita symbol equaling 1 for these three permutations. It equals -1 for these three permutations and 0 otherwise. Let's look at a few of these just to see why this is true, why these are even and why these are odd. So the first one is easy. That's the identity. So there's no transpositions at all. So in other words, 0 transpositions, which would be even. So that's clearly even. Then the next one I want to look at is this one here, 3, 2, 1, 3, 2, 1 here. So if we draw this as a permutation, we have 1 to 3, 2 to 2, 3 to 1. And so that's just a single cycle, a two cycle. So just one transposition, so that would be odd. So that works. Some of the other ones are a little bit harder to see. Let's look at this one here, 2, 3, 1. So we can write that as the product of two cycles, 1, 3, and 1, 2. And we do it in the order right to left. So I've just taken these and I've written them out in detail here. So this is 1, 2, 2, 1, and then 3 to 3. That's this one. And then this is this one here. So we start on the right and we see what happens to 1. 1 gets mapped to 2 and 2 gets mapped to 2. So the net result is 1 getting mapped to 2. So that fits. And then you have 2 to 1, then 1 to 3. So 2 gets mapped to 3. And then finally 3 to 3, 3 to 1. So 3 gets mapped to 1. So the product of these two cycles, where you do this one first and then this one, equals this. It's an even number. of 2 cycles, so this is gives us a +1 for the Levi-Civita symbol. All right, and I'll leave the other ones for you to check, but you need to do something like this for this one here, and then these two are just a simpler case. And then once you know this, the way to remember this is not a theorem, but it's just a fact that it helps you remember. If you take these in order and you shift them to the right, so in other words, you move 2 here, 3 here, and then you move 1 around, and then you shift them again, 3 here, and then 1 to the second spot, and you move 2 around. That gives you the 3 even ones. And then you can do the same if you just take this in reverse order and then do the same shifting I described, you would get the 3 odd ones. That's what I'm depicting here. Okay, so this works even if for n greater than 3, this type of memorization technique. All right, let's continue. There's a relationship to the cross product, and I'll talk about that on the next slide. In 3 dimensions, the Levi-Civita symbol is related to the cross product. Let E1, E2, E3 be a positively oriented orthonormal basis for a vector space. And then let U and V be elements of V. And we want to represent their cross product. So we can do, this is even independent of Levi-Civita, this much here. It's the determinant of you putting the 3 vectors on the top, and then these are just scalars that we put in the second and third row, and that can be written this way here, and here's where the Levi-Civita symbol appears. And this is just giving you a plus or minus sign, which is related to how the determinant gives you a plus or minus sign when you do the computation. So you have this triple sum, and then the ith component of this is this here. So we've just taken it, we fixed the value of I, so this sum goes away. We're just looking for one element, and then that, in terms of Einstein notation, can be written this way here. This implies this double summation. The J was the J and the K was the K, or the 2 summation indices. For n dimensions, we have the following formula that relates to Kronecker delta and Levi-Civita symbols. So we have the product of 2 Levi-Civita symbols for different permutations, and it's the determinant of all these Kronecker deltas. And then for the case n equals 2, we have this. So that's a little bit easier to deal with. So if you recall, the determinant of a 2 by 2 is just the product of this minus the product of the other diagonal. And then for the case of 3, n equals 3, we have this.